right. How are you doing on this beautiful morning? All right. All right. Okay. So, like I said on Piazza yesterday, because attendance yesterday was middling at best, I am doing AI for today and probably Monday and Wednesday next week as well. We'll get back to graphs for like one lecture after that. So please watch the Dijkstra's algorithm lecture. You will not understand the follow-up if you do not do that. So please, by Wednesday, ideally. So today, though, I'm gonna start kind of the module that has to do with how neural networks work. So it's gonna be like, I'll say like a very brief introduction. There's like whole courses about it. I'll try to give you an idea of how they work, both with language and with images. And there's going to be a bit of kind of LLMs and agent stuff next week in the lab as well. So I'm actually going to interrupt the flow in the middle of this lecture to talk about LLMs and agents. It's all going to come together. Sorry. So this is a picture of a neuron. So neurons are cells in the brain. They communicate via electrical pulses. I mentioned it briefly before as well. So basically, what happens is the cell starts generating electrical pulses. That makes it so that, the ion concentration goes up, goes down, and that affects other neurons that also start sending out electrical pulses. So that was picked up by people, starting from like the 70s, I guess, and in particular by Jeff Hinton, who eventually came here. And the idea is there's like lots of neurons in the brain, and the way they work is one starts firing, and as a result, another one starts firing, and so on. And, like to the extent that you think that your thinking and cognition happens in your brain and it's just a physical process, it must be that this is the process of computation. It's like one neuron starts firing, another neuron starts firing, another neuron starts firing, and eventually there's like instructions to your speech center to produce words and so on. So that's the idea. Here's what's known about how neurons actually work in the human brain. It's not actually that much. So we know that in the visual cortex, neurons do work kind of the way that I described.
Businesses get the perfect cards at the perfect price with premium finishes and thousands of.
All right, I canceled YouTube Premium. So this is a famous experiment. It's a little bit grisly. They did get a Nobel Prize for it though, so it's okay. Basically the poor cat is here in the apparatus, and it's being shown different stimuli. So I'm gonna switch to the stimuli. This is the mean guys who are doing it, who got the Nobel for it. So it's shown like this kind of stimulus and so on. And then what was found is that you show the cat different stimuli. So like this moving circle or whatever that's moving diagonally, and one neuron fires. The way you know, and you can hear it.
Black dog seemed to be working.
So if you hear like the noise, this is the neuron firing because there's an electrode stuck in the cat's brain that's picking up on the neuron that starts firing. So that's kind of what's known. And what this means is that in the visual cortex, at least, this computation is happening. So that means that, a photon hits your retina. As a result, a cell in your retina starts firing electrical pulses. As a result of that, different neurons, depending on what exactly is the signal, start firing in your visual cortex, I believe over here. Okay? So the idea that this is how cognition works in general is a hypothesis, but a very plausible hypothesis because, like, how else? So, okay. So, is same. The idea is we have those neurons. It's a graph of nodes. Each node is a neuron, and they communicate between each other. And as a result, computation happens. So we'll come back to this in about 10 minutes. But now I want to talk about the other component of how you make it work. And that's machine learning. So specifically what's called supervised machine learning. Supervised refers to the fact that you have both inputs and expected outputs. So the framework is kind of like this. You start with past data. Maybe you have like 1 million images, and then each image is labeled. And the task is what's in the image, and you know what's in the image because those were pre-labeled. Or maybe you scraped the internet and you just have like images and you have captions because that's on the internet as well. Or maybe you have like past customers, you're like an insurance company or a bank, and you want to predict whether the person is going to pay back the loan that you're giving them or not. And again, you know what happened to predict something for a new customer. Or you have like a patient that's admitted to the hospital and they have maybe like physiological measurements or like whatever chart history. So this is something that I've been working on, like 5 or 6 years ago. And you want to predict what's going to happen with that. So like how, for example, you want to predict like the length of their hospital stay or something. Or you want to predict whether it looks like without intervention, there's going to be a bad outcome. So you want to prevent that outcome, whatever. Right? So you have past data, and then the task is based on past data where you have both inputs and outputs. You have new data where you just have the inputs, and you want to compute the output. So the general idea with machine learning is you somehow take the past data, and then using the past data, you figure out a way to predict what's going to happen with new data. So one of the goals for this lecture is to kind of understand a little bit how that can happen. So, okay, questions so far? Out of curiosity, so how many people like already knew what supervised machine learning is? So most people. Okay, well, now you all know. All right. So here's kind of a way to approach thinking about this. So when you are like in 180 or 190, you kind of have the same thing, right? So like on the test, usually there is like sample inputs, sample outputs. And what you want to do is you want to write something that computes the output for a new input. That's in a way the same task, right? So in machine learning, though, what you're doing is a little bit different in the sense that you're kind of blindly saying, okay, like I am not writing code by necessarily understanding what the problem is. I just have this function that's parameterized. So here's an example of a parameterized function. It's like h with the parameters, theta 1, theta 2, theta 3. And I just want to, like based on past data, like what are theta 1, theta 2, theta 3, that if you plug in a new x are going to produce the correct y. And the goal, rather than what you do in Introduction to Programming, is you kind of understand the problem, and then you say, okay, like here's how to generalize the examples with the understanding of what the problem is. Here you're just saying, well, I'll just find good theta 1, theta 2, theta 3. And as it turns out, in a lot of settings, that actually works. So I really like this slide. I made it a few years ago. So again, kind of what you're supposed to do when you're coding, certainly on the exam, is not to do what's called like shotgun debugging, where you kind of write some code and it doesn't work, and then you say, "Ah, like I'll just change something and see if it works again," right? So, like this doesn't work, and why doesn't it work? Well, because like E here is a local variable, so it doesn't actually double the L outside the function, right? So like a bad approach is to say, well, like I'll just change something a little bit and see how that works out. That's not an efficient way to do debugging. You should just plug it into ChatGPT and it says what ChatGPT. So machine learning, though, does kind of work that way. So you might imagine saying, I have this function that's just like maybe a polynomial. And so this is like a fake example, right? And I'll just say, okay, like I'll try like those thetas and then I'll adjust them and see if that gives me a better output. And in a lot of settings, that turns out to actually work. So not so much with adjusting code. Adjusting code little by little doesn't work that well with machine learning either, although there have been advances on that. All right. So, all right. So here is kind of the formal setting. So we have a training set. So a training set, we ordinarily say kind of training examples are fixed dimensional vectors. If they're not fixed dimensional, there's ways to make them fixed dimensional. So here, like the output is like input, is x1, the output is y1. For input x2, the expected output is y2, and that And then the hope is you take the training set, you plug it into whatever machine learning algorithm is, and the machine learning algorithm essentially tries to find like a good theta such that h theta of xy, xi is approximately equal to yi. It can't be exactly that, depending on what h theta is exactly. And you're trying your best on the training set, and the hope is that if it works on the training set, it would work on the test set as well. All right, and if it does, then great. So that's kind of the formal setting. Does that notation all make sense? All right. So a brief interlude on gradient descent. So this is basically how you implement the idea that I outlined here, which is like find a theta such that for most i's, h theta of xi is equal to yi, right? So here's an idea. So we set up what's called a cost function. So that's a function of the theta. And we set it up in such a way that this function is going to be small when h theta of xi is a good approximation of yi, and it's going to be large if not. The way it's set up is we just say, like sum up the square differences between h theta of xi and yi for every training case I. And then, like, if you predict perfectly, this is 0, right? If you predict really badly, it can blow up by a lot. And then our goal, remember, is to find the theta, so the parameters theta, such that this is approximately this for most i's. So that just means like find a theta such that j of theta is small. Make sense? So this is not the only way to set up a j of theta, but it is one way to do it. This, of course, assumes that the y's are like numerical. But there's ways, again, to like measure, like, is h theta of xi different from y, or is it not different? All right. So that's the goal. How do we do it? So how do we find essentially the minimum of J with respect to theta? The answer is gradient descent. Technically, like you all know how to do it for some settings, right? So how do you find the minimum of something? Well, take the derivative, set it to zero, solve the equation, right? The problem is that for something like that, you can't actually solve that equation in closed form, right? So like for most of this, look at this. This is like a huge function, right? This is a function of theta, but it's like a huge formula. You cannot just compute the derivative and set it to zero and expect to solve it. Just the algebra is not going to work out. Does that make sense? So how can you do it? Well, gradient descent. So here's a picture of what we're going to do. So the picture represents J. So J is the z-axis. And then if you imagine that the theta is like two-dimensional, then whatever, like the x is theta 0 and the y is theta 1, right? And then the J is going to be like something like this, some kind of surface. Does the graph make sense? So then gradient descent is saying we'll start with some kind of guess, and then we'll try to find a minimum. How do you find the minimum, this kind of thing, if you just start with an initial guess? Well, you have an initial guess. You can say, okay, like, what's the gradient at this point? The gradient, as you now know, is the vector on the surface that points downhill, right? So what you would do is you'd start with an initial guess, and then you say, okay, like, which way is downhill? I'll just go that way a little bit. I'll evaluate again. Which way is downhill? I'll go this way a little bit again, and so on. If you keep doing that, eventually you'll end up at a local minimum. Does the concept kind of make sense? All right, let's implement it. So all right. Yeah, I'm sorry I did not get to actually post this code. I'll post it after the lecture, but it's going to be like brief enough that you can actually just copy it as well. Oh no. All right. So here's the goal. So we'll have a function f, or let's call it j. And it's going to take theta as the argument. And we also have, so we all have, you know, an x that's going to be fixed. So like we'll just make something up. Oh, so I'm going to say, for example, return, you know, theta 0 times x plus theta 1 squared minus 5. Right? I get to say whatever I want. So now my goal is to find a local minimum of j. with respect to theta. Make sense? So how do I do it? I guess the initial value of theta. This is just a guess. And then I compute the gradient and I follow the gradient. So let's compute the gradient of J. So we're going to compute grad J. Going on. All right. And we'll follow the gradient. So follow the gradient means theta 0 is minus equals G0 and theta 1 minus 0 G1. And we'll do some kind of constant here that's maybe very small. So again, going back to the picture, what are we doing? We are computing the gradient of J. So that means the direction that's downhill on this surface. The way we do it is we compute the partial derivatives, right? And then once you have those, so sorry, I kept saying I think that the gradient points downhill. It of course points uphill, but if you minus it, that's going to be downhill, right? So we compute the direction of the gradient. That's where you go to go uphill. Reverse it, that's going to be the direction to go downhill. And the gradient is just the partial derivatives. So here, sorry. So here, what we can do is we can just literally compute it, right? It's not hard. So what's the gradient of J? Well, so the partial derivative with respect to theta 0 is what? Well, are you like done with calculus or something? So what's the J by d theta 0? That's really not hard, guys. It's right there. Anyone? So I have this formula for J, and I want the partial derivative of J with respect to theta 0. Was it not on the test or something? Okay, like the answer is it's X, right? So anything that doesn't involve theta 0 just gets zeroed out, and the coefficient for theta 0 is just X. So dj by d theta 0 is just X. All right, was that hard? I don't know. Why didn't? Okay, is anyone object? Does that make sense? Does that not make sense? Okay. Why didn't anyone say? So okay. Okay. Well, try again. What is dj by d theta 1? That's right. Yeah. That's right. So 2 times theta 1. All right. Is that now good? So that is all it is. I did not plug in X, so that's why. All right. So that's all it is. So we can now say, okay, so we have our J, we have our grad J, and our procedure is guess whatever theta, and then keep updating theta by moving theta in a direction that would make it go downhill. All right. So this would be whatever, like grad descent. So I'm going to guess theta. I'm going to guess like whatever, 6, 7, right? And now, and I have no idea how I taught before this year. So now we can keep just doing this. I'll set C to something small. I'll compute G. So X needs to be something. So X is like the fixed data. Theta is the thing that we're trying to adjust, right? And we are going to do it in a loop. Whatever, like 100 times. So we computed G, and now we'll update theta. And we'll update this theta as well. And we'll see how that's working out for us. So I'll just print the current value of J. J takes theta and X. And the idea is that if that works, then it should become generally smaller. There's no guarantee, but should be fine. All right, so we started with theta being 6, 7, and that gave you a J value of whatever, 49.8. And as you see, it's going down. It's not going down too fast, so we'll maybe make the updates larger. And here, I think we're still not there. So I'll just do more steps. And here it's, doing okay. So trying to find a smaller and smaller minimum. So eventually it would converge. So here, like it is a parabola, so it still hasn't found the minimum, but eventually it'll get there. Okay. So does this kind of make sense? So this is the direction in which if you move theta, that's like the direction of steepest ascent, right? So the direction in which you go to go uphill. And then we just keep updating theta. So the picture is over here. All right, questions? All right, so one subtlety, and that's kind of often missed, is what I said is technically slightly inaccurate, and that's because it's true that the gradient is like the direction of like the steepest ascent, but technically this is 3D. The gradient here is 2D, right? So the gradient would be dj by dx and dj by dy. So when we say that the gradient is the direction of steepest ascent, what you really mean is it's a direction on the plane where if you move the theta 0, theta 1 in that direction, then you're going to go uphill. The actual vector that points uphill is not the gradient because it's not, the dimensions don't even match. The gradient, the direction is 3D, the gradient is 2D. what is the direction of the actual vector that points uphill, that is homework. Figure it out. I'll tell you on Monday. The answer, not the gradient, the dimensions don't even match. Does that make sense? Did they tell you that in calculus? Well, I'm telling you, I mean, like it's like obviously true because the gradient is 2D and the direction there is 3D. So yeah. So okay, so figure it out. It's not very complicated, but they for some reason it's not in Stewart, I think. So okay, we have done that. So okay, so the framework here was to remind you. We set up the supervised machine learning task where we have a training set and a test set. And then we said, well, just set up some kind of H theta, maybe some kind of polynomial. Polynomial not going to work very well, but some kind of H theta. And then adjust the theta so that H theta computes the right thing on the training set and hope that it's going to work on the test set as well. So here's kind of a concrete example. So let's say that you have a bunch of images with names attached to them. And what you want to say is, the input is the image, meaning the pixels. And the answer should be, does the image contain a picture of noted Canadian musician Justin Bieber, right? So, okay. So Justin Bieber to a computer looks kind of like this. So if you like if you take the values of every pixel, something like that. So in particular, and we've done it a bunch of times, if it's a grayscale image, what you ordinarily do, and we've done it in the lab as well the other way, is you say, okay, so like the grayscale values ordinarily are like 0 to 255. And then you just read off the image, row by row. And you get this fixed dimensional vector if you started with a 4x4 image. Right? So that's kind of the representation of a picture. Looks like this. So now we again have, our training set. So, the x's are going to be the pixels. So that's like a vector. And the y's in the general case are going to be labels. So those could be like strings, like names. It could be like 1 if it's Justin, 0 if it's not, something like that, right? And then in the test phase, we have a new input vector that's also an image, and we want to assign a label. So I'm going to do like the simplest possible thing that you can do. It actually fits in the framework that we discussed, but it's not trainable with gradient descent. This is called 1 nearest neighbors. So here's an idea. You have the training set, and you have a new input. And what you do is you just say, for the new input X, so for this picture, does it look like this? Does it look like this? Does it look like this? Find the most similar image, and then just look up the label on the most similar image. So those people, for anyone who doesn't know, those are the Beatles, right? So this is John, and this is George, and this is Paul, and this is Ringo, okay? And this, I'm not actually sure that you can tell just from the picture, but this is Paul and this is Paul, okay? And the idea is if this image looks the most like this one, then the answer is, well, if this is Paul, then this is Paul as well. So this is called 1 nearest neighbor. So you take a new input, you just figure out the example where you know the answer that's the closest to the input, and you just look up the label. All right. So one thing to note here is that does this work in terms of the math in the framework from before? Well, kind of, yes. But the theta in this case is like the entire training set. It's not just like a few numbers. It's like you have a function. The function is just look up which image is the most similar, and output the label. So the parameters of that function is just the entire training set, because you need to know what the entire training set is in order to figure out what the output is for this algorithm. Does that make sense? So it's a little bit unusual in that way. So how do you know whether two images are close or not? Well, this is something we discussed a little bit in ESC190. So you could just take two vectors. So remember, the images are now fixed dimensional vectors, right? So you can just say, like, what's the distance between the endpoints? And that's just going to be like the Euclidean formula, right? And that's one way of saying, like if two images represented by vectors are the same or like similar, then the Euclidean distance between the endpoints of those vectors is going to be small. So kind of the picture here is like this picture of pole and this picture of pole should be close together. Another way to do it, same thing that we did in 180, is rather than look at the distance between the endpoints, you can look at the cosine of the angle. That usually works better. So one way to think about it is two images which are just like one is a darker version of another. Those are going to be basically vectors that point in the same direction, because you multiply every pixel intensity by a constant. What happens, you get a brighter or darker image, but the contents are the same. But the distance between the endpoints could be very large if one image is like dark and one image is light, right? Looking at the angle between those solves that problem. And for the angle, we have a formula that we already saw in 118. Or you might have seen in high school. Does that make sense? So we take this kind of thing, and depending on the situation, like one might work better than the other. It's not guaranteed that the angle is better, actually. And the algorithm is you just compare the inputs to every training image, you get the label. So, okay. So that's one way of doing it. We haven't gotten to neural networks yet, but now we do have neural networks. So here's like a concrete sample task that I'm going to run with. I didn't actually have like Beatles face images, so we have those people. So here's the simplest possible thing that's technically a neural network that can do this job. So this is a picture that just represents the formula up there. It's nothing more than that, but it's a convenient way of thinking about it. So the formula is we have 6 outputs. So we had 6 people in the training set. So 1 output per person. So those would be Z1 through that 6. And then we also have the formula for computing each ZK from the inputs X. So if the image is 64 by 64, we flatten it. It's a 4096 dimensional vector. And then the formula is like this. So we say, in order to compute Z, we compute X1 times the weight on this edge, and then plus X2 times the weight of the edge that connects X2 to Z1, and then X20 times the edge that connects X20 to Z1, and so on. So this is this formula. It's like multiply each xj, so each intensity of the pixel, by the corresponding weight on the edge. Right? So the 1 here is always constant. You'll see why later. So here it's just like wjk times xj. The k for zk is also constant. So that just means that it's like a dot product between x, and you can think of it as like a slice of the w. All right? So it's like x1 times w111, and then plus x20 times w121, and so on. You also have a b term that's plugged in here that also goes into this. Is there anything interesting happening at noon or something? And you have this formula. So there's also a transformation. So this is like the sigma. There's various formulas for the sigma. So this is just like a monotonic function that you plug this thing into. So another way of thinking about it is what we're basically doing is we're computing a dot product between X, the image, and W1 everything K in order to compute ZK. All right. So that's that's for now just a formula. The thing about it is now it's a parameterized function of the X. So we can now say, well, what I want to do is I want for it to be the case that if I plug in a picture of person 1, then Z1 should be high and all the other Zs should be low. And then if I plug in a picture of person 6, then Z6 should be high and everything else should be low. And that's the same framework as what we had done before with H theta. So the theta now is the W and the B. And we can just say, okay, we have a framework, gradient descent, for adjusting parameters so that the function outputs whatever we need on the training set. And this is something that's, something that's adjustable. Does that make sense? So the other way of thinking about it is you can kind of say, okay, so this is like a very simple setting, but you can say, okay, so like the X's are the cells on your retina that are activated by, light that's been reflected off the face of Justin Bieber. And then, whatever, like Z3 is the neuron that gets activated when you see, the picture of Justin Bieber, in the same way that the cat has a neuron that starts firing when it sees the circle moving diagonally. All right. So that's kind of the analogy. We'll get to more complicated neural networks later, but that's the idea. So when you're doing face recognition, what do? Well, you plug in the X and you get the Z output. So ordinarily, the way it works is you compute 6 outputs, and then you just look which one is the highest. If ZK is the highest, you say it's probably person K. Why would it work? Well, because you made it work. You made it so that on the training set, it usually outputs the right thing. You did it with gradient descent. And this, kind of remarkably actually works. So I have 6 minutes, which I'm going to use in order to start talking about language. That's an interlude because I want to start doing language early next week. So the flow is going to be slightly broken, but hopefully that's okay. So, but questions about any of this so far? Is this good? All right. So, okay. So how does language work? And I should say kind of the face recognition thing, what I described totally does work. Modern ChatGPT, if you paste the image into it, it doesn't quite work like that. It works more like language, but kind of the details for that you'll have to see in 2 years, assuming it's still the same in 2 years' time. So all right. So how does the language model work? So what does a language model do? It takes some context, so a prompt, and it tries to predict the next word. That's what a language model is. The way it's set up is very similarly, except the X is now not an image, it's the context. And you make it fixed dimensional somehow. And then you have a vocabulary of words. Usually it's not words, it's segments of words, but whatever. And then you do the same thing. You're saying, if it should be that Z1, then it should be word 1, that Z1 should be high. if it should be like word number 6 in my vocabulary, then Z6 should be high, and so on. So most people have more than 6 words in their vocabulary after they've taken praxis. So there would be like whatever. Like if you're talking words, you would probably do like 10,000 English words. If you do like subwords, it's more. But that's details. Okay. So rather than 6, there would be more outputs, but the principle is the same. Does that make sense? So the one thing that you would ask is, okay, like you said, like context or prompt, how is that fixed dimensional? So that's a little bit complicated to explain, and there's details and there's multiple ways of doing it. But here's the big picture. So you already saw that there are ways of embedding words into vector spaces. So representing each word using, let's say, a 4096 dimensional vector. That's about what people actually use, a little bit less usually, right? So that's one word, and you already know one way of doing it. There's more sophisticated ways of doing it as well, but that's just one word. So what about like a context, like a whole prompt? That's like multiple words and not even a fixed number of words. Again, there's more sophisticated ways of doing it. That's what I'm about to say, but what I'm about to say also works. You could just add up all the word vectors from the paragraph together. That's going to be the same dimension. You just add them up, and that's going to actually work pretty well. So this is probably counterintuitive if you're thinking about it as like vectors in 3D. Like, why would like adding a bunch of vectors represent any information at all? Aren't you ruining it? The answer is in high dimension, not very much. So imagine that word 1, dimension 67 of word vector 1 is very high. Everything else is low. And then for word 2, dimension 6767 is high. So you add those two together, that actually preserves the information that it's a paragraph that has both word 1 in it and word 2 in it, right? Because, there's lots of dimensions. Most of those dimensions are like close to 0. And then for word 1, dimension 67 is high. And for word 2, dimension 6767 is high. So the sum is going to actually contain the information that you need. Again, not an ideal way of doing it, but you can do it. It actually does work. All right. So, okay. So now that we know that there is a way to represent the context, this is what an autoregressive large language model is. They're all autoregressive. Autoregressive just means you predict one word at a time in order to get the output. So this is basically what your ChatGPT or whatever does, is you give it the prompt. It starts with a prompt. It also has a system prompt, whatever. And then it generates W1. The way it generates it is it does have something like that inside where the output is, like, is it word 1? Is it word 2? Is it word 3? And so on. Then it picks one. And then it just plugs prompt W1 back into itself. And it predicts the next thing, so W2, and then it predicts W3, and so on. So autoregressive just means it generates W1, and then we plug prompt W1 back into it. This is the new context. It also has W1 in it. So now you get to predict W2. Make sense? And remarkably, it turns out that it works. If the kind of underlying H theta that predicts the next word is good enough, it produces coherent text. We'll start talking about what actually made it work 5 years ago on Monday. I will see you. Bye.